everyone. I hope you're safe and doing well at home, not too bored. For today, we're going to do a couple of different things. So we're kind of wrapping up our equilibrium unit. And so we're going to go over a couple of questions and some homework. We're going to talk about one more quick concept that we haven't talked about yet. And then we're going to talk a little bit about how we're going to wrap up this unit. So first, we're going to go over the question that I posted for you all based on Monday's class. Okay, so here's the question that we are looking at based on Monday's class when we talked about the effect of temperature on equilibrium. So you all watched a quick video that showed this equilibrium between this cobalt chloride compound, which is blue, and this cobalt water compound, which is pink. And what you saw in the video is that they started with this nice pink solution, and then when they heated it with a Bunsen burner, the side that got heated turned blue, right? And the question was, okay, well, is this forward reaction then endothermic or exothermic? Cool. Well, based on what we saw in the video, right, you saw that when the reaction is heated, it turned blue, which means that this pink compound must be turning into this blue compound, right? So the reverse reaction must be happening more than the forward reaction, right? In order for the pink compound to turn into the blue compound. So we know based on the color change that the equilibrium has shifted left. It's shifted back towards the reactants, right? We also know that when you increase temperature, right, the equilibrium is always going to try to counteract that change. That's Le Chatelier's principle. So the equilibrium is going to try to use up the extra heat that's being added to the system. So if the equilibrium is shifting one way, right, it must be shifting to use up the heat. So in this situation, equilibrium is shifting left. That must mean that heat is over here on the right of the equation, right? Because the equation is using up that heat in order to make this reactant. So the heat is here on the right of the equation. Okay, now if heat is on the right of the equation, the forward reaction as written must be exothermic because the forward reaction is producing heat. A bunch of folks in their responses said something along the lines of like, the reaction must be endothermic because it's absorbing heat, right? It's true that the YouTube that you saw on YouTube was absorbing heat, right? What was physically happening was that the system was absorbing heat. But also the reaction that was happening was the reverse reaction, right? This pink compound was turning into the blue compound. And so the reverse reaction, what you're seeing in the videos, you're seeing that the reverse reaction absorbs heat and is endothermic. Right? That means the forward reaction, which was not predominantly happening, this happening at a slower rate than the reverse reaction. So the forward reaction, if the reverse reaction is endothermic, the forward reaction must be exothermic. So the forward reaction here is actually an exothermic reaction. All right, I also wanted to quickly talk to you about some of the homework that you've been working on. So you all worked on this worksheet for homework due on Wednesday. I want to just really quickly talk through some of these problems. Right. So for problem number 1, we're looking at what effect increasing pressure would have on equilibrium. We know that pressure, when you increase the pressure, the equilibrium always shifts to try to adjust itself to relieve that increase in pressure. So if you have a reaction that has gases in it, the equilibrium is gonna, and you increase the pressure and you're kind of squashing the gases together, the system's gonna kind of shift to adjust to alleviate that pressure. And the way it does that is it shifts to the side that has fewer moles of gas, right? The fewer moles of gas you have, the less pressure they're exerting. So for 1A, right, we've got 4 moles of gas on the left and 2 moles of gas on the right. So if you increase the pressure, the equilibrium is gonna shift to the right. Just quickly going through the rest of these, right? For B, you've got 5 moles of gas on the left and 3 moles on the right, so equilibrium is going to shift right. For C, you have 2 and 2. So the equilibrium is actually not going to shift at all. Increasing the pressure will have no effect on this reaction because both sides of the equation have the same number of moles of gas. The same is true for D. Increasing the pressure has no effect. And then for E, if you increase the pressure, it's going to shift your equilibrium to the left. Good. For number 2, we're looking at the effect of temperature on equilibrium. For 2A, they've given you delta H, and we see that it's a negative number, right? That's telling us that this reaction is exothermic. So we can think of heat as really being a product in this reaction. Good. If we increase the temperature, we're increasing the amount of heat. That's essentially the same as adding a product, right? Since the reaction is exothermic, we're treating heat as a product. And so the reaction is going to shift to use up that heat, meaning it's going to shift towards the reactant side. NH3 is going to react with itself to create more N2 and more 3H2, right? And by doing that, it's going to use up that extra heat that we've added. So this one, A, is going to shift to the left. B, we're looking at an endothermic reaction. We can see that because heat is written in here on the left of the arrow. If we have an endothermic reaction and we increase the temperature, the reaction is going to shift to use up that extra heat. So C and H2O are going to react to make CO and H2. The reaction is going to shift to the right. For C, we have an exothermic reaction again, right? When we increase the temperature on an exothermic reaction, it's going to shift towards the reactants. So this is going to shift left. Same with D. E, they've again given us delta H, but now this time delta H is a positive number. There's no negative sign. That tells us that this reaction is endothermic. Heat is really a reactant in this reaction. You could write in plus heat over here if you wanted to, right? Since heat is a reactant, if we increase the temperature, it's going to shift to use up the heat. It's going to shift to the opposite side of the equation. So it's going to shift to the right. Okay, for number 3, we're looking at the effect that each of these different changes has on the equilibrium. If we add H2, there's going to be more collisions between H2 and I2. The system's going to try to use up that extra H2, so we're going to shift to the right. If we remove I2, there's going to be fewer collisions between H2 and I2. And so to compensate, the system's going to try to make more I2. And so your equilibrium is going to shift to the left. If we increase the temperature, we have to look at delta H. Delta H is positive. That tells us this reaction is endothermic. So since this reaction is endothermic, we can treat heat like a reactant. That means if we increase the temperature, the system's going to try to use up heat, and it's going to shift towards the products to the right. If we increase the pressure, we have to look at the moles of gas. The left-hand side has 2 moles of gas. The right-hand side also has 2 moles of gas. So increasing the pressure will have no effect on the equilibrium for this chemical reaction. And then if we add HI, we're adding a product. The equilibrium is going to shift to use that up. So it's going to shift to the left. Good. 4 and 5 are a little more conceptual. 4 is asking us to explain Le Chatelier's principle based on collision theory. There's a couple of different ways to talk about this. I think the simplest way is to say when you increase the concentration of a reactant, right? So if you increase, for example, like H2 in this equation, there's more collisions between the reactants. And so the rate of the forward reaction increases. And so temporarily, the forward reaction is happening more than the reverse reaction. So in this example, right, H2 and I2 would be making HI faster than HI is reacting backwards to make H2 and I2. Eventually, the system's going to resettle in equilibrium. But before that happens, the forward reaction is happening faster than the reverse reaction. And so what happens is the 2 reactants make more products. And so your equilibrium ends up making more products, meaning it's shifting to the right, to the product side. In contrast, if you increase the concentration of one of the products, now you've got more collisions between products, which means the reaction rate of the reverse reaction increases. And so the reverse reaction is now temporarily faster than the forward reaction. If the reverse reaction is faster than the forward reaction, that means a bunch of the reactants are going to react to make more of the products. You're going to use up reactants and you're going to make more products. And so your equilibrium shifts left. We can also talk about what happens if you remove something, right? If you remove a reactant, then there's going to be fewer collisions between your reactants. So if you remove a reactant, the rate of the forward reaction slows down, it decreases. And so temporarily, the forward reaction is happening slower than the reverse reaction. And the reverse reaction is going to make more reactants faster than the forward reaction makes more products. And so the amount of reactants will increase. So if you remove a reactant, the amount of reactants ends up increasing. If you remove a product, the rate of the reverse reaction decreases because there's fewer collisions between the products to make reactants. So if you remove a product, the rate of the reverse reaction decreases. That means temporarily the forward reaction is happening faster than the reverse reaction. And so you make more products. Good. And then looking at question 5, right, if heat speeds up all reactions, both forward and reverse, which it does, we talked about that when we talked about reaction rates, why does it affect equilibrium? The idea here is that heat speeds up the forward and the reverse reaction, but it doesn't speed them up the same amount. Whichever reaction is endothermic needs heat to happen. It needs more heat to happen than the exothermic reaction, right? And so the endothermic reaction gets sped up more when you increase the temperature. It's affected more. So if you increase the temperature, the endothermic reaction is going to speed up more. The exothermic reaction will speed up a little bit, and the endothermic reaction will speed up a lot more. And so the reaction ends up shifting. Basically, the endothermic reaction happens more than the exothermic reaction. And so the reaction ends up shifting towards the side that doesn't have Q in it, right? As the endothermic reaction happens, the side that has Q like makes more of whichever side doesn't have Q. Good. All right, I'm back in PowerPoint because I wanted to review, or not review, I wanted to talk about one more concept that we haven't talked about yet, which is the effect of a catalyst on equilibrium. So take a minute right now to think about, we've talked about catalysts a little bit before. Take a minute to draw a reaction coordinate diagram, right? That's where you have energy on your y-axis and reaction coordinate or time on your x-axis, right? So energy and then either reaction coordinate or time on the x-axis. And I want to see that with and without a catalyst. So pause the video, take a minute to do that on your own first. It's a good review. You should all do this, test it out, actually do it. You should have something that looks a little bit like this, right? They've done a kind of fancy version of showing like a extra squiggle for a catalyzed pathway. That's fine. You don't have to show that. You can show it with just one hump as well. Either way is fine. We talked a little bit about how when you add a catalyst, the rate of the reaction increases because the activation energy has decreased, right? Remember, the activation energy is the energy to get from the reactants to the highest point, right? From here to here, that'd be your activation energy. With the catalyst, the activation energy is lower. And so it is easier for the reactants to react. They don't need as much energy in order to react. Cool. It's worth noting that a catalyst lowers the activation energy for both the forward and the reverse reactions, right? Here's the original activation energy for the forward reaction and the activation energy with the catalyst. For the reverse reaction, here would be the original reverse activation energy, and then the original catalyst reverse, not original, the catalyzed reverse activation energy would be here, right? So the catalyst has lowered the activation energy for both reactions, and it's done so equally. And so both reactions are going to speed up the same amount when you add in a catalyst. The forward reaction speeds up, the reverse reaction also speeds up the exact same amount. What that means is that the rate of the forward reaction has increased, but the rate of the reverse reaction has also increased, and they're still equal to each other. So your reaction is still at equilibrium if you add a catalyst. In other words, catalysts have no effect on equilibrium. They speed up the forward reaction and they speed up the reverse reaction the same amount. And so overall, there's no change to your equilibrium. There's no shift between the reactants and the products. Cool. That was the last actual piece of content that you all need to know about equilibrium for this class. So we're actually done talking about equilibrium. That said, I think it's great if you all can review equilibrium a little bit. And so in order to do that, you're going to be working on a review project. You're going to make a video in which you review some of the key concepts of equilibrium. You're going to do that in a group of 2 to 3 people. Tonight, that's Friday, you are going to shoot me a quick email with your group members, or if you're not sure who to work with, you'll shoot me a quick email saying, hey, I don't know who to work with. Right, and I'll help you find group members. There's a whole bunch more details that I'm going to post on Google Classroom. This is like the most key information. I'm going to post a description that has all of the exact questions that your video needs to answer. You also need to include some example problems. There's a bunch of different ways to make videos. You can do kind of what I'm doing right now, where we have like PowerPoint and we're kind of going back and forth between PowerPoint slides. You can do that. You can just have a video of yourself talking. That's fine too. You could also video yourself writing on a piece of paper, and like we wouldn't see your face, we would see your hands, and we would see what you're writing down and drawing pictures, whatever. That works great too. There's some really cool videos that work that way. Whichever way you want to do is totally fine. You can mix and match and do like some of each. Any of those is fine. What you do have to do is every group member has to participate in the video somehow. So you're going to need to like work out who's going to record which part, record your parts. You're going to need to combine it back together to make one video. And then you'll send that to me by next Friday. Again, I'm going to post a more detailed description of the assignment on Google Classroom, so make sure you read that. And post a comment if you have any questions, because I definitely want to make sure to answer any questions you might have. Awesome. Okay, so that's your review project. The review project is going to be a great review for your practice test on Friday. So we're not giving any tests during these couple weeks before spring break. But if we were in normal school right now, you would be getting a test on equilibrium. So instead, I'm going to give you a practice test, right? You're going to take it just like you would take a real test to test out how well you know equilibrium. And so that's going to happen next Friday as well. So I won't be posting a video next Friday. Instead, I'm just going to post the test. You're going to take the test, and then we'll see your score and go from there. Cool. In summary, I've included a question right here. I'm also going to post this on Google Classroom. This is a nice question that kind of summarizes all the different effects that we've talked about in equilibrium. So you're going to answer this. This is going to be your classwork for today's class. All right, and then one last thing that I didn't mention yet is that by now you should have checked in a couple times with your lab partner. If you haven't already, please make sure to reach out to your lab partner. I want to make sure that everyone is keeping up with the class and it's just doing okay, is getting to talk to someone their own age, not just like stuck at home with their parents and their siblings. So please reach out to your lab partner. I'm going to post a quick Google Sheets poll thing on Google Classroom. So one of the two lab partners for each pair just needs to reply to that and let me know that y'all have talked together. If you haven't heard from your lab partner by now, shoot me an email, let me know, because I want to know what's going on so I can reach out. So make sure you do that. And I think that's everything. So for today, right, you're going to fill out the lab partner thingy, right? You're going to answer the classwork question on Google Classroom. And by tonight, by Friday night, right, you're going to email me your partner for the project. And you're going to start working on the project over the weekend. It's going to be due a week from today. So it's going to be due Friday, April 4th. And we'll have our practice test then as well. All right. I hope you all have an amazing weekend, and I will see you again on Monday. Bye.